All right, Algebra 2, we are in Chapter 3, Section 3.2 today, applying the properties of rational exponents. A little bit of a review first. If you remember, when you have the same base, which is a 4, you add the exponents. 3 plus 8 is 11. Okay, next, when you have the same base, which is the 8, and you're in a fraction mode, you subtract the exponents. So 5 minus a negative 4 is in fact 9. Okay, simplify the expression. I need to take that 48 and split it into numbers. I'm trying to find any perfect squares that multiply to 48. So 2 times 24, 2 times 12, 2 times 6, and 2 times 3. Every time I get a pair, I can take it out of the radical. So I'm taking 1 2 out and another 2 out, and there is a 3 left in the radical. So my simplified expression is 4 root 3. I could also have taken 48 and done 4 times 12 and 4 times 3. So I have a pair of 4s taken out. 15 times 30 times 15, a few ways that we can do this one. We can simplify it first. 2 times 15, 3 times 5, so I can't do anything there. So I'm going to go ahead and erase that. So I need to go ahead and multiply the radicals first. So I'm going to say 30 is the same as 2 times 15. And I'm multiplying that by 15. So underneath the radical, I have 2 times 15 times 15. So I have a pair of 15s, therefore that 15 can come out, and the 2 is left underneath the radical. Okay, simplify the expression. I cannot subtract radicals unless they have the same number underneath the radical. So here I'm going to go, let's see, 16 times 5. I know 16 is 4 times 4, so that's going to be 4 root 5 because I have a pair of 4s that comes out of the radical. Here I have 4 times 5, 2 times 2, so 2 root 5. Now I have a root 5 for both of them. That means that I can, for lack of a better way to say it, subtract the coefficients. So 4 minus 2 is 2 root 5. So here are all the rules. We're now doing rational exponents. The rules that we've had before stand true. When I've got the same base, I add the exponents, and I'm multiplying them. If I have a power, I multiply the exponents. If I have a power outside of parentheses, I distribute the exponents. A negative goes to the denominator. Division or fractions, I subtract them. And a power for a fraction, I distribute it evenly. So these properties hold true. Okay, if you don't have them memorized, you may want to save this page to look at when you're doing your problem set. The big difference here are all of my examples, or most of my examples, are going to be fractions. Okay, so just get your calculator out and have fun with your fractions. But the rules that we've learned in the past hold true. It's just now we're working with fractions. So use the properties of rational exponents to simplify the expression. Here I have the same base as 7, so I need to add those exponents. So 1/4 plus 1/2 is 3/4. Okay, I have a power to a power, so I distribute that. 1/2 times 2 times 1/3 times 2. So that gives me 1/2 times 2 is 1. And 4 to the 2/3. So that actually is my final answer, 6 times 4 to the 2/3. just because I don't have to write that 1 down. Okay, still working through. Now I'm going to distribute that -1/5 if I would like. I do see that these are both 5, so I'm actually going to factor that out first. So 4 times 3 all to the 5th power. I can't lose that -1/5. Oops. I now have a power to a power, so I can multiply these. So I get 4 times 3, 5 times 1/5 is 1. So I have -1. That is, when I have a negative exponent, I drop it to the denominator. 4 times 3 is 12. And I have my final answer. Here, this is like a 5 to the 1st power. I have the same base as 5, so I actually subtract those exponents. 1 minus 1/3 is 2/3. And here I have a power to a power. These are both raised to the 3rd power, so I'm actually going to collect those first. So they're both to the 3rd, and then I raise that to the 2nd power. 42 divided by 6 right here is 7 raised to the 1/3 raised to the 2nd power is 7 to the 2/3. A mammal's surface area, S, in square centimeters can be approximated by the model S equals km to the 2/3, where m is the mass in grams of the mammal and k is a constant. The values of k for some mammals are shown below. Approximate the surface area of the rabbit that has a mass of 3.4 kilograms. I have no idea why this is a thing. You'll have to ask our biology expert. But yeah, that is sort of awkward to talk about surface area of mammals. Whatever. So let's go ahead and try this one. I've copied the formula over here, so I'm going to write the model. And then we had K for the rabbit is 9.75, and we're given 3.4 times 10 to the 3rd to the 2/3. Okay, I sort of have a distribution of powers. So 9.75 times 3.4 to the 2/3 times 10 to the 3rd to the 2/3. That gives me approximately 9.75 times 2.26, because we learned how to do that in our calculator, times 10 squared, which is approximately 2,200 centimeters squared. Okay, let's practice a little bit. Use the properties of rational exponents to simplify the expression. Again, I'm going to distribute One-third times 3 is 1, so I get 5 times 7 to the 3/4 as my answer. Here I've got the same base as 2, so I'm going to add 3/4 plus 1/2 and get, 2 to the 5/4. Division, this is to the 1st power, so I'm going to take 3 to the 1 minus 1/4, which is 3 to the 3/4. Here it looks like I have the same exponent, so I'm going to go ahead and use that to my advantage. So 20 divided by 5 is 4. I know that 4 to the 1/2 power is 2. 2 to the 3rd power is 8. That was sort of fun. That was sort of tricky though. Use the information in example 2 to approximate the surface area of a sheep that has a mass of 95 kilograms. Let me get what the K value is for that example. Sheep, K is 8.4. So 8.4 times 9.5 times 10 to the 4th grams raised to the 2/3. So 8.4 times 9.5 to the 2/3 times 10 to the 4th to the 2/3. That all simplifies down to approximately 17,500 centimeters squared. All right, so we did examples 1 and 2. Let's look at example 3. Now we're going to use the properties of radicals. Here I have the third and the sixth properties can be expressed using radical notation when m equals 1 over n for some integer n greater than 1. So here, I'm going to take my problem and I have a product property of radicals. That means if I have I don't even care, third root of 4 times 8, it's the same as the third root of 4 times the third root of 8. The third root of 8 I can simplify to 2. So I really get 2 times the third root of 4. Okay, same here. If I have a big root over a fraction like 4 over 8, I can say that's the same as the third root of 4 over the third root of 8, which is the third root of 4 over 2. So I can use those product property of radicals and quotient property of radicals to my advantage. So let's try it here. They're both third root. I'm going to use the product property to simplify. So I've got the third root of 12 times 18, which is the same as the third root of 216. And in lesson 3.1, I learned that 6 times 6 times 6 is 216. Here I've got the same root, so I'm going to go ahead and put the radical over the whole fraction because 80 divided by 5, I believe, is 16. Yep. So that'll give me the fourth root of 16, and I do know that 2 times 2 times 2 times 2, 4 times, is actually equal to 16. That was a nice example 3. Moving on to example 4, simplest form. A radical with index n is in simplest form if the radicand has no perfect nth powers as factors and any denominator has been rationalized. That means if I have a fraction, I can have no radicals in the denominator. And the whole thing, all radicals have to be as simplified as possible. So if I look at this first one, write the expression in simplest form. 135, I don't know. My perfect triples are 2 cubed is 8, 3 cubed is 27, 4 cubed I believe is 64. Yep. 5 cubed is 125, etc. So I want to figure out if 135 is divisible by any of those perfect cubes. So I'm going to go ahead and divide by 8. That doesn't work. Divide by 27. Hey, that works. So 135 is the same as 27 times 5. So I can take the cubed root of 27 and the cubed root of 5, and I get 3 cubed roots of 5 as my simplest form. So here, fifth roots, that's a bit harder. I don't know, 2 to the 5th power. I need a perfect fifth. Something raised to the 5th power. So 32. 243, well, that's not going to work. I wonder if I can change this denominator into something with a 32, because I cannot have a radical in the denominator. I'm not allowed. Now, back when we first learned how to do square roots, if I try to simplify this one, I know I can just multiply by square root 2 over square root 2, because this thing right here is equivalent to 1. So if I multiply the top and the bottom of the fraction by square root 2 over square root 2, remember I just multiply across the top, I get square root 2 over square root 2 times square root of 2 is square root of 4. Square root 2 over 2. And that is my rationalized radical. That's all well and good, but I really don't want to do this. Oh, that's not right. I don't want to do that either. Back it up. I don't want to multiply by 1, 2, 3, 4. I need 5 of them. So fifth root, fifth root, fifth root, fifth root. Same thing on top, because I'm really multiplying by ones. And these are all equivalent to 1. Okay, this up here is really the same as this down here. I don't want to do that up there. That's way too difficult. I need to figure out how to get that denominator into something that is a fifth root. And I do know that 8 times 4 is 32. So if I multiply my numerator and my denominator, so let's go ahead and start again. Give myself some space. If I take fifth root of 7 over the fifth root of 8, and I multiply it by the fifth root of 4 over the fifth root of 4, this fraction right here is equivalent to 1. Multiply across the top and the bottom. I have the fifth root of 7 times 4 is 28, and the fifth root of 8 times 4 is 32. But we just said that the fifth root of 32 is 2. And right there, I have my simplest form answer. That's sort of tough. Okay, we'll get it with some practice though. Okay, last example, then we're going to practice a few. Like radicals. So radical expressions with the same index and radicand are like radicals. To add or subtract like radicals, use the distributive property. So I have the fourth root of 10 plus 7 fourth roots of 10. This is really 1. Right? I don't really use distribution. I sort of say we're collecting like terms. I've got 1 fourth root of 10 and 7 fourth roots of 10, so that really gives me 8 fourth roots of 10. When they say use the distributive property, that means I'm going to factor out the fourth root of 10, and what's left is 1 plus 7, which is 8. So however you'd like to think of it, it's fine with me. Just make sure you stay sort of consistent. I've got these things as exactly the same. That means I can add the coefficient. 12, 8 to the 1/5 is my answer. 2 plus 10 is 12. Okay, here I have to do some work first. Now, 54 is equal to 2 times 27. I know I want a 2 there because that's what that one is. And we're to the level of math where things aren't super duper tricky, just a little bit tricky. So I can actually change that third root of 54 to 2 times 27. Third root of 2. Now I can go like this. This one right here simplifies to 3. And remember, I have a 1 here. So 3 minus 1 is 2. There we go. All right, we're going to practice these guided practice, and then our lesson is done for today, and we'll finish it tomorrow. 4 through to 27, 4 through to 3. Let's see. I know I can do 27 times 3. That gives me 81. And I've memorized that 3 times 3 times 3 times 3 is 81. So the fourth root of 81 is in fact 3. Just checking. Yep. Here I really like to do this. Third root of 250 divided by 2 is the third root of 125, and we reviewed a few slides ago that 5 times 5 times 5 is 25. So we have our answer. Simplify the expression. Here I need something in my denominator that's a perfect fifth root, and we just learned that 2 to the 5th power is 32. So the fifth root of 32 is 2. So if I can multiply that fraction by something that will give me 32 in the denominator, life is grand. So I'm going to I'll rewrite this. Fifth root of 3 over fifth root of 4 times the fifth root of 8 over the fifth root of 8. That gives me 3 times 8 over 4 times 8. So I have the fifth root of 24 over the fifth root of 32. And we just said the fifth root of 32 was 2. Cool? Awesome. Now I'm adding. I bet I need this radical to be a 5. So I do know that 40 is the same as 8 times 5. So I can do cubed root of 8 times 5, which I'm going to split up. Cubed root of 8, cubed root of 5. I know that the cubed root of 8 is 2. There's a 1 in front of this one. So when I add those, I get 3 cubed roots of 5.